Okay, so welcome everybody. It's almost 5 after. I can still hear a bit of an echo, but we'll cope with it. So I'm Mike Morrow. I'm the president of the St. John Center, which I think everybody here and everybody online probably knows of the RESC.
I didn't know you were president.
You didn't?
No.
Okay, well, there you are. It was a useful thing. Well, it wasn't that useful thing to say anyways, but so I'm going to start with an acknowledgement. We respectfully acknowledge the territory in which we gather as the ancestral homelands of Beothuk and the island of Newfoundland as the ancestral homelands of the Mi'kmaq and Beothuk. We'd also like to recognize the Inuit of Nunatsiavut and Nunatukavut and the Innu of Nitassinan and their ancestors as the original people of Labrador. We strive for respectful relationships with all the peoples of this province as we search for collective healing and true reconciliation and honor this beautiful land together. So I'm just going to, I think most people that are here are members. I just point out that we have lots of benefits of RESC membership, and we're actually going to talk about some of them after Ivan's talk. I'll just point out if people aren't getting them, we do get a weekly newsletter and a monthly bulletin, and one of them you need to sign up for. One comes automatically, and I forget which one's which, but if you want to get one and you don't know how, let Randy know at info@stjohnsresc.ca. So I'm going to let Ivan start because he needs to go off now and mark exams, and
read a thesis. Then I get
a lot of stuff to do. He's a busy guy, and so our speaker tonight is Dr. Ivan Booth from the math department. He's going to talk about observations in an expanding universe. We're very lucky to get him in the middle of marking exams, and I'm especially grateful to Ivan because I basically assigned this topic to him. I got in touch with him several months ago and said, I don't understand this. And I thought he would. So I'm really grateful that he took this on. Ivan did his BSc in applied math and physics here. And 1995, got little windows on top of other things. He did his PhD at Waterloo, got that in 2000. He was an insert postdoc at the University of Alberta. I guess, was that with Werner Israel?
Don Page.
Don Page, okay, well, another name to conjure with, in 2002. And that's probably showing my age when I jumped to.
Yeah, he retired about 5 years before that.
Okay. So he, in September, he came here and he's now a professor in the math department. And so with no further, the title is Observations in an Expanding Universe, but I'm going to let Ivan explain why that's interesting. So I'm going to stop sharing and I'm going to mute myself. And
now the fumbling begins on this end.
Good luck.
Okay, can you hear it okay there, Andy? Okay, so yeah, so Mike asked me to do this a few months ago, and I said, okay, I think I can do that. I hadn't actually heard of this phenomena before. And so, but it seemed like it was cosmology, it was GR, it seemed like I'd be able to do it. So as part of the research for this one, I found that there was an XKCD cartoon about it. So that's always a good way to start. As we'll see at the end, this XKCD isn't really quite right. There's something a bit wrong with it. But I don't know, maybe people can see what it is already, but we'll see it towards the end. So the idea is that if you look, you make observations back to the early part of the universe, and there's a certain point as we look at things as they get farther away, and an object the same size, a standard size galaxy, as it gets farther away, it gets smaller and smaller and smaller, like the perspective you'd expect it to do with perspective. And then beyond a certain point, they start to get bigger again. And they call it the angular diameter turnaround or turnover point. And so that's what I'm going to be talking about, trying to explain why this happens. And I guess in this, the XKCD here, the conceit of the XKCD is these are Samsung Galaxy phones. So it's supposed to be like a Galaxy. That's the joke, I think. And I guess they've also got them set up so these are supposed to be like the time, right? And, and so, 13 billion is bigger than 12 billion, is bigger than 11 billion, bigger than 10 billion. And then the 10's are about the same, and then they start getting smaller. I guess they should start getting bigger again around 9 or 10. I don't know, I can see an 8 up there. I didn't look at this that closely. And there's also some joke here about how the battery's almost dead, but I forgot what that joke was. It's like a joke that Randall Munro made. Okay, no, so yeah, and so here, so he says here, brightness and redshift adjusted to keep the phones visible. I didn't notice that bit. So this is the bit that's wrong, of course, because this one, 13 billion years, it should be big, but it should also be redshifted. So it isn't. So anyway, so I started thinking about what I was going to talk about with this. And then I've kind of worked out what was happening. And then I was trying to figure out how to do my figures for it. And then I was thinking about what else I needed to say. And then I ended up backing up. So I decided in the end, I was going to start off with sort of I was going to organize this around sort of a brief review of cosmology and the different things that happen in cosmology because we're in an expanding universe that probably, don't really seem, they seem kind of a bit unusual because there's so many things in physics or in relativity especially, because our intuition is based on us living on Earth, moving at slow speeds and small gravitational fields with the Earth, with the world basically unchanging around us. That's our intuition. So when those things don't hold, strange things happen, things that we think are strange. Okay, so here's my title. And as lots of you have heard me speak before, and so as you know, second now, oh boy, I'm not an observer, and what's going to be disappear on me. And I'm also not a cosmologist. So, there's the not observer bit. Not a cosmologist going to show up. What's happening here? Oh, there it is. And I'm not a cosmologist. So I'm a theorist, right? I'm a black hole theorist. And so, there's a lot of stuff here that I may not. I think what I'm going to say is right, but maybe the depth of my knowledge may not be as deep as one might hope, but we'll see. Okay, so let's just think about some of the basic principles of cosmology. So the basic principle of cosmology, and this is sort of going back, hundreds of years, is that the universe is pretty much the same everywhere. Space is homogeneous. Oh, so I guess I shouldn't walk around because I've got to be near my mic. Space is homogeneous. It's kind of the Keplerian principle. So we kind of think space is pretty much the same everywhere. This, of course, is, in some sense, obviously not right for cosmology because, there's something that's quite different from being on Earth and, sort of being sort of in between the galaxies. And, there's all these great structures. And it turns out that as large and large, as higher and higher you look, at the larger and larger scale you look, there still seems to be structure. But, still for the basic idea in cosmology, and most cosmologists would agree that at the largest scales, you can treat things as homogeneous. There are people who argue about this, and that space is isotropic. So isotropic is kind of like homogeneous, but it means it's the same in every direction. So it's not like there's not some preferred direction through space. So you can imagine what's the good example maybe would be, say you had a cylinder, right? There's the preferred, that's not quite right, but it'll be close enough for us now. If you have a preferred direction, kind of like going up and down the cylinder along the length of it, you can imagine you've got some arrows pointing up and down the cylinder, but it's the same as you go around. So you could be the same everywhere, but still have some directions that were different from others. So isotropic means you don't have preferred directions. And so if you make those assumptions, then there are just three, I'm wandering around again. There's just three possible geometries locally. And they are, you can have like space can be flat, so basically Euclidean. Space can be sort of spherical, which means it has positive curvature in a certain GR sense. So then you kind of would imagine our space, our universe is like the surface of a three-dimensional sphere. That's when I say three-sphere, I mean the surface is three-dimensional, right? So if you use like x squared plus y squared plus z squared plus w squared equals 1. Or it can be, and they call that closed, or it can be hyperbolic. So in which they call open. Now, so it's not going to matter too much about these because basically we know now our universe is flat. Observations suggest it's flat. So we don't need to worry too much about these. But so in addition to these, we have the kind of the same thing everywhere, but you also have a situation where, I guess I should be pointing with an arrow here so people online can see it, You also have a scale factor. So it's easiest to see the scale factor for the closed one because we can think about spheres. And so, you know, the idea is you often see in cosmology, people talk about a balloon and like ants living on top of a balloon or galaxy floating on top of a balloon. And you can, so the scale factor kind of tells you that your universe is getting bigger or smaller. And in cosmology, basic kind of standard model cosmology, that's all that can happen. Scales can increase or decrease. And I guess an important thing to think about when you're thinking about, an important part of this is these scales are kind of the stretching of sort of space itself, right? So as the universe expands, that doesn't mean that this monitor here is going to expand, because it's essentially it's kind of a very weak force trying to cause it to expand. And the electromagnetic forces and quantum mechanical forces that are holding this thing together are way stronger than that. So you don't get, like regular objects don't expand, it's just the empty space regions that expand. Or contract. And so this is, we're going to talk about this a bunch of times. So we're going to have this scale factor A, which tells you the distance. So if you're thinking about it was a sphere, you can think of that scale factor as kind of like the radius, or the square of the scale factor being the area on the surface of the sphere. And so the universe is the same everywhere, but it can change in size. Okay. And our universe is flat. Okay. So that's what space is like. Now, what is matter in cosmology? There's just three types of matter in the standard models again. There are other models that add extra things, but the basic models that, you know, that cosmologists kind of assume are the foundation of our universe is just three types. There's dust. And so dust is things that only interact with gravity. So dust, in this sense, are things like galaxies or superclusters of galaxies. They all count as dust particles for a cosmologist. All the dark matter would be dust. Everything on this scale is just anything that's interacting with gravity. And you're looking at these super large scales, so gravity is really the only force at those kinds of scales. Again, there's models of cosmology where people argue about whether maybe there could be magnetic fields at large scales that affect things, but I think they're kind of a minority. Okay, so there's an example of a few types of dust, right? All of that's dust, right? That's dust. Everything's dust there. From everything that we can see is dust, basically, and all the dark matter is dust. Okay. So then the other thing that you have is radiation, and this is mainly photons, so the cosmic microwave background. Sometimes neutrinos will get lumped in here as well. And so the difference between dust and radiation is dust, again, it only interacts with gravity. Radiation, there's some pressure involved in it as well. So if you try to compress it, it'll kind of push back at you. So you got the cosmic microwave background radiation is the pressure, is the radiation. And then you have dark energy, which is the cosmological constant. So you just got these three things, and each of them has slightly different properties, but each of them is basically that scale factor with some power on it, kind of tells you about the densities of these things. So for dark energy, I just didn't really have anything, so I just have the black screen as my example of dark energy. Okay, and so then that's what we have in our universe. So for our universe, we have the dust, which is, you know, all our visible matter, all dark matter. That's about 30%. Radiation is about, you know, 0.1%, 0.01%, and the dark energy is about 70%. Okay, so you have so these things at this stage, this is really like pre-general relativity. You're just talking. I mean, you don't need general relativity at this stage. You can talk about the universe being the same everywhere and the shape of the universe without any general relativity. You can talk about the matter content without general relativity, and then when you combine that geometry with the matter content and general relativity, that'll give you the equations that tell you how your universe evolves. Okay, so that's where you put time in. So probably lots of you know the Einstein equations. So this very complicated series of coupled nonlinear PDEs. But when you've made all these assumptions, like these are really physicist assumptions, right? These are kind of spherical cow kind of assumptions. Because once you've made all these assumptions, the Einstein equations reduce to, I think this is the only equation in here, a single differential equation. So that's the scale factor. That's the thing that tells you, like, you know, how distances between objects. So the time derivative of the scale factor squared is just equal to, you know, we've got some constant. That constant doesn't matter. I could have just probably shouldn't have written it there. And you have the dust, some constant associated with the dust divided by a cubed, some constant associated with the radiation divided by a fourth, and some constant associated with the cosmological constant. And, you know, for people who haven't done calculus for a while, A dot will mean your scale factor is greater than 0. That means the universe is expanding. A dot less than 0 would mean it's shrinking. A dot greater than 0 would be accelerating. A dot less than 0 would mean it's decelerating. And so what we see in our universe is, okay, so 25 years ago, people thought we had expanding and decelerating. Then with as of 25 years ago, people realized that this bit was wrong. 25 years ago, they thought the cosmological constant contribution was 0. And so they thought they were decelerating and expanding. Now we know it's expanding and it's actually accelerating because of this term here. Okay, so there's some physicists in the audience. So if you're a physicist, you kind of look at these equations, right? And you think, oh, well, if A was really, really small, this term is going to be the dominant term. If A is really, really big, then these terms kind of drop out, and this term is the dominant term. And then you've both cases there, you've got easily solved differential equations. And then somewhere in between, all three of the terms are going to contribute. And that's sort of where we are at the moment. So in the early universe, when this term was the main one, radiation was the most important thing. Well, I guess the really early universe, you had inflation, but that's like super early. The mid-universe where we are now is basically dust and dark energy doing everything. The radiation is almost meaningless. And in the late universe, this is where dark energy dominates, right? Ultimately, the cosmological constant, you know, drives everything apart, rips everything to pieces, that kind of thing, right? And so I guess that's where we have. So around, you know, around this stage and here, you've got the radiation dominated. Back here in the quantum fluctuations and inflation, that's sort of before we're talking about here. Then you've got, this is the mid-range, and then later on, we end up with the dark energy dominating everything. So if anyone has any questions along the way, just feel free to yell out. Okay. So our universe is expanding and accelerating. Okay. So what do we know about how do we know things about the universe? And so one of the kind of the key observations that people make is, well, okay, I'm going to get to that on the next slide. Here, I'll just start first talking about Doppler shift. So this are little black dots in the center of some sources, and they're sending out radio signals at regular intervals. Or you can think of these as wavelengths of radio signals. So, you know, so here we have the green guy as an observer, and the black guy sending out the signals. And you can imagine that every time one of these little wave fronts goes past the green person, they measure a wave going by. And so they see a frequency of waves going by. So for basic Doppler shift here, now we're not really thinking about cosmology or anything, we're just thinking about, you know, particles moving around. If your observer is moving in towards the source, then of course you cross all those wave fronts more quickly, right? So by the time they go through there, that one's still going, right? And if you're moving away, then the wave fronts have got to catch up with you. And so you see a lower frequency of waves going past you to correspond to a longer wavelength. So when you're moving towards, let's just move that out of the way. So I got all kinds of stuff covering up all kinds of things. Oops. Okay. So I guess we can look at here. So when you're moving towards things, you have this blue shift, right? And so you see your wave shifted towards the blue direction. When you're moving away, you have your wave shifted towards the red. And the frequencies, I've got this written down wrong here. The frequency there, that should have been a greater than, and this one should have been a less than. So all of these things down here are wrong. That should have been the other way around. Yeah, that one says blue as well. I just like copied and pasted and made a mess. So just ignore that. I guess I can just kind of drag that up over it so we don't see it.
Experienced teacher.
I should have spotted it earlier though and covered it before. So, okay, so if you're moving towards things, you have a blue shift. If you're moving away from things, you have a red shift. That's kind of the basic thing. And that would be like, that's like ambulances, hearing an ambulance siren, hearing a plane go overhead, a helicopter fly by. It's, if it's relativistic, right? So you're moving closer to the speed of light, the details change, but it's still the same basic picture. And it also applies if you're in a universe and you're sitting in the universe and the universe is expanding, the same kind of thing's going to happen. If the universe is expanding, you're going to see signals towards you being redshift. Okay. I guess we got these things happening again. Oops. Okay. Okay, so one of the basic, observational things, and apparently this goes back to the maybe you may well know this better. Apparently, it goes back to the late 1800s, or the kind of the mid late 1800s, like 1860 or 1870. People started making Doppler observations of stars, and I don't know what they thought the lines of the stars were at the time. Does anyone know? Because there are shifts in the kind of atomic energy levels, right? The absorption and emission lines. So different processes within a star have different nuclear processes are happening. And the results are, they'll expect from light from the star will either have emission lines or in this case, absorption lines, right? So you see these gaps. And so when they looked at stars, when you look at stars, if they're moving, if they're moving towards you, you see they're shifted in one direction, shift towards the blue. I guess that's maybe what's happening there. And if they're moving away from you, they shift the other way. And so they were measuring something like this in the 1800s. I don't know what they thought was happening. I kind of just skimmed the Wikipedia article on that. So I'm not sure on that. But then, the big result was in the early 1900s. This was Hubble. And I guess, I'm sure there's other people involved as well. What they started to realize was that the absorption lines shift systematically with distance. So he was looking at things that were relatively close by, so where they could still measure distances, some of them with parallax even, some of them with maybe with Cepheid variables. I'm not sure they're doing that, but they had methods of measuring some distances. And what they saw was that, I guess I didn't mean them all to come in at once, but it's okay. What they saw was that roughly distance seemed to be proportional to the redshift. Now, the redshift is just the observed wavelength of light divided by what the emitted was, because what the process is. From the pattern of lines, what process it was that emitted things. And then you see that shift and you subtract 1 from it. That's just the way it works. And it turned out that this measurement of the redshift was sort of proportional to the distance. Now, here's an example of how these things look. So this isn't like all the points on a dotted line on a straight line, right? This is a scattered points, and they're looking at correlations. And so I don't think this is Hubble's data, but this is some data. So you can see they kind of, it's kind of going in the way, but then you got this mess of the Virgo cluster, which is screwing that all up. But imagine if that wasn't there, things would look better. And, so this isn't going to be perfect because, of course, there's other things, there's complications here, right? Not only things aren't just all kind of moving with the cosmological medium, right? They are also moving by themselves as galaxies orbiting, moving towards us, moving away from us. If you're looking at quasars or something like that, then you have massive gravitational redshifts because there's a redshift associated with gravitation as well. So there's all kinds of details here. But overall, this was a general picture that we saw. That the farther away something was, the more redshifted it was. Which suggests, at the time it suggested that as things were farther away, and remember, we're thinking, you guys all know this, we're thinking as you look at things that are farther away, what you're really doing is looking into the past, right? And so it appears that things in the past are kind of sort of appear to be moving away from us. And this relates, the redshift, in fact, relates to the scale factor in a similar way to it relates to the wavelength. So one way you can think about this is, the popular explanation you'll often see is that as the light travels through space in between, it kind of gets stretched out because space is stretching. I guess that's kind of right. I don't really think of it that way, but that is what people will often say. Okay. So that's the sort of the picture. So this is one of the effects, right? Because the universe is expanding, we see these redshifts in, stars, galaxies, everything. Okay. So this is kind of the, the smoking gun of the expanding universe, I guess. So we see that, things are redshifted, and as you go farther and farther away, they get more and more redshifted. And so the interpretation is, your universe is expanding. It's expanding kind of the same everywhere. That's from the cosmological assumptions. And so like, if this is, if at this point it's kind of expanding this rate, this point is expanding this rate, then as you add them all together, you kind of add all those assumptions, all those expansions together. And as you get further and further away, things sort of farther and farther away are in some sense moving away more quickly. So I think I know what the next slide's going to be. Okay. So here's the redshift again. So as a relativist who spends my time thinking about black holes, I'm much more interested in like times and light years than redshifts. Redshifts aren't really intuitive for me. But I mean, redshifts are the thing that's observed, right? I mean, they're the thing that makes sense to talk about because you look at a telescope, your redshift is what you measure. You don't measure distances. And in fact, the distances are a bit weird. So roughly, and I guess I should also say back here with the Hubble law, there was an approximate equals in there. So this is just like the first approximation. As you get to larger and larger distances, this rule breaks down. This rule changes. And so I guess, sort of 50, 60 years ago, people were trying to measure this constant, the Hubble constant. We're just basically doing it by looking at graphs like this and trying to do best fit lines. I guess we know nowadays the Hubble constant isn't a constant, right? We still call it a constant, but it changes in time. And there's other kind of more sophisticated ways of measuring it. But there's a more complicated relationship here. This is just kind of the small distance approximation, I guess. Okay. So here's roughly how it goes. So redshift of 1 is about 7. If you look at, okay, so now how do you get this distance, this association between redshifts and distances? Well, so for Hubble, he had multiple ways. And, for things close by, you can measure things through parallax, or you've got these standard candles, and you can measure things, then you can measure the redshift, and you can try and get this relationship. And that relationship between the redshift and the distances, or the distances in the past, this is kind of the thing that tells you what cosmological model you should be looking at. This is the thing that tells you what your relative contributions of different types of matter are, how the expansions work. All of this stuff is like kind of data that feeds into these equations. I've been kind of mixing it all together here, but like this is a key thing. This for different, if you have different kinds of cosmological models. So like if we had, 30% dark energy, 70% matter, dust, and, or, 40% dust and another 30% radiation, these relationships would be different, right? These are model dependent. Okay, but these things are the things you measure. These are the things that, and then these things are sort of like theoretical quantities derived from it. So we thought, so this is, based on the standard cosmological model, these are the redshifts that correspond to distances, right? Our universe is about what, like 14.5 billion years old or something like that. And these redshifts kind of increase a lot as you go back into these, as you go back closer to 14 billion. So we've got this. So this is the time that the light has been traveling as a function of redshift. And then you have this one here, the distance, and these correspond to the distances to the objects now. Now, if you're a relativist, you think, what are we talking about here? Now, like distances now, this is not something you really want to be talking about in general relativity, because one of the kind of the key messages, and people who see my talks about black holes, one of the core messages of general relativity or special relativity is that there's no such thing as a universal instant in time, a universal notion of simultaneity, right? So all you can say is you can look at, whether you can send light signals between things, you can tell whether something happened first or, before or after something else. There'll be a whole bunch of things that you can't get light signals between, so you can't say, and it's physically meaningless to say which one happened first because you got this maximum speed of propagation. So if we're talking about something that is 1 million light years away or 23 billion light years away or whatever, however many billion light years away, now this is like this is a physically problematic statement, right? Like what can this possibly mean? I mean, obviously it means something that won't be in this chart. But the reason you can do this is that cosmology actually does sort of break this basic idea of GR, because the basic idea with GR is that you have the vacuum And it's kind of invariant under all these different kinds of transformations. And so this is kind of one of the reasons why you can't associate these universal notions of simultaneity, right? It's what a now is. But if you have a cosmology and you've got a perfect cosmological model, a dust model, it actually furnishes you with a physical idea of now, because all this dust, for example, is evolving with a cosmological medium, but it's not actually moving, right? The medium itself is moving and dragging things with it. So as these particles move away from each other, right, as the universe expands, they're not moving in the sense of, with, how would we say it? They're not moving relative to the medium. The medium itself has changed. This is the idea where, where you have the ants on the balloon and the balloon is expanding. The ants move apart, even if they're all sitting still. And so there is a physical notion. Well, okay, interesting point. Is it a physical notion? If you believe the cosmological model is valid everywhere, then you have a preferred notion of what an instant is. And that instant would be this way you slice time so that none of the particles are moving, apart from with a cosmological medium. And so that's what people are talking about when they have these nows. And I think maybe I've got to, no, yeah, okay, I just said that. So here's kind of what you'd think, and I'll just have to move this out of the way again. Oops, that's not obvious. Okay, let's put it up there for now. Okay, so here we have a, kind of a one-dimensional universe, I guess. We have this line, we have this notion of time. And so as time's evolving, we have a bunch of, labeled particles in the universe. This is like the Andromeda galaxy. This is the Virgo cluster. I don't know if they're not in the right order there, right? This is the Earth. This is the sun, whatever, right? And so what happens is as the universe expands, that's not even right if these are the Earth and the sun. But anyway, okay. So what you've got the universe expanding and the particles are moving with it. And so what this first column measures is the light travel time. So how much time would have elapsed? I guess even that's kind of problematic. How much time would have elapsed between when the signal was emitted and when the signal was observed? Then the distance to the object now is, you say, okay, if my model was perfect and I look back and I know where that particle was, 7 billion years ago, then if my model was perfect, then it would have evolved up to this point now. And then I would measure along this distance here, and that would be my distance. But this is really quite a physically meaningless measurement to make, right? Because it's not, there's absolutely nothing you could actually do with this measurement, right? It's not, you can talk about it if you want to talk about distances, but it's not really, it's a very weird kind of thing. I hadn't really thought about it until I was writing this talk. Anyway, so, basically in cosmology, what you can do is you can see redshifts. And those redshifts, you can see objects as they were when the signals were emitted, right? And then, so you can say what was happening, in this galaxy 7 billion years ago, then if you pretend it just evolved forward according to a particular model, then you can say, oh, and this is the distance that it was away from me now. But whether that's maybe, I'm not even sure why you would want to say that, but people do say it all the time. Okay, so there's a bit of a complication there. Because, you've got billions of years and billions of light years of travel. Okay, so that's kind of just an aside. Oops, I'm down here. So, let's kind of think about how things work. So now imagine you've got a flashlight, you shine it out, it's kind of got a 90-degree arc on it. And you're sitting at the middle of some universe. This is where it's static, right? And you're kind of looking at how your light evolves in time. These are cartoons now. I spent like about 2 hours today trying to get a nice, clear, calculated thing that actually kind of really made sense, but it was, in the end, I went for cartoons. Okay, so, light is expanding out. And, as the beam goes out, it gets larger, right? The wave front gets larger. The front of the light gets larger as it moves away. And kind of the edges are kind of moving on straight lines. Okay, so in an expanding universe, you think about what's happening is that, and again, this is going to be a cartoon here. There's going to be lots of criticisms we could all, well, I can certainly make about my next figure, but it gives some of the ideas. So if the universe was expanding, you think about the light, well, the light is still going to travel kind of at the speed of light because it's got to, right? But this whole thing is expanding. In particular, these distances will be expanding, the distances between like along these arcs. So my next picture, this is kind of, again, it's a cartoon, but in some sense, this is what happens. So as your light moves out, as your light moves farther and farther away, the distance, instead of being like 2 pi times delta theta, is going to be more than 2 pi delta theta, because as you move away, your light is kind of, your universe is expanding, and so that light front is getting much larger than you would expect it to be. So that's the expanding universe. And we also need a contracting universe for some reason, well, in order to answer Mike's question. So for contracting universe, you got the same thing. So let's see, will it pause here? I don't think we'll pause. Okay, so as your light as you fire your light away, it starts out moving away, right? Because if you're really in close, and the light is just going to seem like it's a flat space, and your light starts, and your wavefront starts moving apart. But then as the universe contracts, then ultimately this wavefront gets kind of pulled back together, and may even come back, and could even come back and focus. Okay, so this is the motion of the universe, which is changing what the kind of the length of these arcs here. I struggled for a while thinking about how to draw this. I decided this was the best way. All of them were slightly wrong. I decided this was the one that was slightly wrong that still conveyed the message better. Okay. So that's light in an expanding universe. So the radial expansion is normal the speed of light, but the angular expansion gets scaled by that scaling constant, that A again. Okay. So now let's think about the size of an observed object. I think we're getting close to the end here now. So this is from Wikipedia. I put quotation marks around the credit here because this is really not a very good diagram. But I was putting this diagram in around like 4:30 today, so I didn't have time to do anything better. Okay, so what does it mean when we say something's a particular size? I mean, the sun's not even round here, right? It seems very strange. Okay, size on the sky. So what we do is, you're looking at something and you have that angular diameter, right? So this, you're looking at it in the sky, is up there, and you're kind of looking at it and you measure the distance, the angular distance between the 2 points. So that's how we measure the size of an object. And, in regular life, then these objects are all the same size. The objects that are farther away have these smaller angular displacements. Right? So this one is, I tried making it kind of redder as they went farther away, so it would be a bit like a redshift. This angle is smaller than this angle, which is smaller than this angle because this one's closer, so it's got a bigger angular displacement. Okay, so now we're going to do another kind of physicist kind of trick here, because I thought this was the quickest way to try to get to this. So if we're thinking about a contracting universe, a universe that's expanding forwards in time, you can imagine your universe, you just flip time around, then your universe is contracting. This is what we want to do here. Okay, so here we have our universe, and it's kind of going back and forth, right? So now it's going forwards in time, expanding. Now it's kind of going backwards in time. Or no, okay, forwards in time contracting, backwards in time expanding. That looks like, well, this is okay for our purposes. Okay, so then we think about what's happening here. So this is kind of, you can imagine each of these is going to be a object to look at. I guess I can pause this, can't I? There we go. So you can imagine that. Now imagine you're this observer sitting at the origin looking out at things, right? So as you look out at things, these things at these distances all have the same angular displacement, right? And so we go over here. You can measure this angle in here, right? This will be some angle delta theta. And then as you're going, this is going backwards in time, right? Because, you're moving farther away, so you're looking things backwards in time. And as you look backwards in time, you're going to see the objects that are farther and farther away that subtend the same angle will be getting larger and larger and larger, which will correspond to things of the same size would correspond to smaller and smaller angles. And that goes on for a little while. But then, because the universe was shrinking as you went further and further back, at some point, this turns around, right? Because the contraction of the universe has sort of overwhelmed, the contraction of the universe going backwards in time has overwhelmed the attempt of the light rays to move apart from each other. And so as you go further and further back in time now, this is for the same angular diameter, you saw things that were getting bigger and bigger and bigger, and then they get smaller and smaller and smaller. And this would correspond to the expansion, right? So if you were trying to get things all the same size, then as you go back here, you're going to get smaller and smaller angles, and then the angle will get bigger and bigger as you go in the same size. And so for our universe, it turns out that this is around Z 1.5. So from things about 9.4 billion years ago, things start to look bigger. Okay. And so this thing here, this point here, where these angular diameters flip and start changing, this is the turnaround distance, they call it, or the turnover distance, they call it in different places. Okay, and then so this is back to the diagram. Here, I was going to come back to the diagram and criticize the redshift, but then, of course, he notes up here that the redshift was adjusted to keep the phones visible. Okay, that's my best attempt, Mike.
Okay, well, thank you very much. Lots in there, and we probably haven't all got all the subtleties right off the bat, but I think if we run into this idea again, I know what I'll think about is your cartoons, your animations. I think that is very helpful to me. So
Good, I spent a long time on.
yeah, thank you very much. I appreciate it. So we have questions. I'm sure Ivan can take a few questions before he goes off to Mark. And people online, if you can indicate.
Can I stop sharing?
No, don't
Okay.
don't stop yet.
Okay.
Let's see if there's any. So and you're not an observer, and you were sort of just looking at the idea, but and when did they first did they know this was going to happen, or
Oh, yeah.
so they were expecting this?
Definitely, yeah. So you can look at, because when I was reading about it, I was looking at my old textbooks, right? So, for example, Weinberg from the 70s talks about it, Misner, and Wheeler talks about it. They've known that this doesn't depend on, this is only factor of having an expanding universe, right? So if the universe is expanding in this, so it doesn't matter whether there's dark energy or anything like that. They've known. Yeah,
So it's got nothing to do with the acceleration or any of that stuff.
No, it doesn't even need to be accelerating. It just needs to be expanding. You still have this. Yeah. So yeah, textbooks in the 70s, and those are the oldest ones I have. They talk about this. Yeah.
So is what's new the fact that we're actually seeing galaxies that far back?
Maybe. Yeah. That could be what it is. Yeah.
And Chris probably knows that too.
Certainly, like in the 70s, from the 70s, further back, and quasars were seen as points.
Right.
There was no, hey, this is a galaxy.
Yeah.
That is one of between 2 and 3.
Yeah.
Right. So we were the era of seeing 7, 8, or 9 or whatever.
Yeah.
That's all we want.
Yeah. I mean, I guess Z equals 3 would be enough, but I guess they didn't have the angular resolution for anything of that size.
I use it as fuzzy cutoff, or you can almost get away with thinking it's 1 to 1 until you get about Z equals 3.
Yeah.
And the divergence, like backward time and distance, is just
Yeah, that's true. Yeah, maybe at 3 it may be
yeah.
maybe minimal. But
Yeah. So there's a question here from Sue Hart, which is related to this. It might be as much for Chris as for you.
Okay.
She said, how does the Webb telescope figure into all of this? And because it is starting to see these.
Yeah, I think the record right now is that is 13.
I think that's about right.
Which is
Yeah.
way outside of, linear, et cetera, et cetera. The thing about Webb is seeing galaxies that are fully formed way too early in the universe. That's a whole other kind of fish.
Yeah, so I don't know, so, I don't know if Sue can hear you because you're. I don't know if she can hear me because I'm probably muted, but Sue, can you hear it?
I
Can
couldn't
you
hear that
me
very
now?
well, actually.
Uh,
Sorry.
yeah, so what Chris said was that, what did Chris say? Say it again.
Can I remember? Yeah, Webb is seeing ostensibly fully formed galaxies, way too early in the universe.
Yeah, so the issue with Webb is that it's seeing galaxies that are too evolved too early. So
100 million.
they are bigger, and certainly Webb is seeing this phenomenon probably better than anything else has so far, but
Yeah, I would think that maybe, yeah, they're bigger and more detectable by Webb than they would be on.
yeah, so they're,
They're certainly seeing structure and seeing the gravitational lines next to the nearby clusters helps you to see more structure too, so that's something.
yeah, and I think that Webb forced people to sort of revisit this idea and realize that this was now going to be something they had to take into account.
Yeah, maybe.
And I think that's
Probably why it's kind of been around that recently then.
yeah, that's sort of what I sort of ran into and what motivated me to ask
Okay.
you about it.
The only things that were visible at all in the 70s were at Z equals 2 or 3 were points.
Yeah.
Now we've got full-fledged galaxies at Z equals 10 and more.
Yeah, so Sue, what Chris is saying is that in the 70s, galaxies that far away looked like points, but now you can actually see, you know, the actual, you can see that they have some size, and that's, so we have to think
Yes.
about this, or something
Yeah,
else to think about.
I have picked up some articles.
Oh, I'm not
talking
hearing you,
about-
Sue.
Oh, didn't I mute it? Oh, okay. Can't you hear me? Can you?
Yeah, we've just said we've got, okay, go ahead.
Okay, no, I was just saying that I had read a few articles very quickly about how, you know, the Webb telescope was seeing unusually big galaxies. And I wondered if that was part of this redshift phenomenon that Ivan was talking about, or is it just that it's a better telescope and we can see more?
I think that's different, right? So
Okay, yeah.
So they,
Yeah.
I mean, this is a really well understood phenomena. So actually, when I was reading about this, there were people saying, oh, is this the reason? No, that's not the reason. The unusual thing is like what Chris was saying is that they don't expect galaxies that size to exist
No.
that far back. I think that's the issue there. I think.
That's what I picked up as
Yeah.
well, but I just wondered. Okay, well, thank you very much for that clarification. Thanks. Great talk, by the way.
Thank you.
Not that I could quite understand all the math, but I'm working on it.
Jim, did you have a question? I thought you did. Oh,
No,
Just something I wanted to ask about the galaxies that are being farther back that are fully formed that have more redshift. Is that why? Because they have the higher redshift. Is that why they think they're farther back in time? Is that the reason redshift? Is it,
Yeah, that's I mean, you know, there's
just wondering,
that's the basic idea. Yeah.
wondering if like we always think we're in the middle of the universe where the expansion is happening in every direction that's going away from us. But what if we're on one side of the universe and we're actually looking through the middle and going towards the other side of the universe, which would have much more redshift? Wouldn't that be the solution to the problem?
Well, I guess the idea is that there is no, you know, the idea would be there is no center, right? Just like there's no really center to a plane, right? You have a plane, an infinite plane, there's no center to it, right? So any point can sort of think of itself as being like the center, or any point to think of it as being near an edge, and it kind of wouldn't affect.
Like there must have been like some center point, you know, if there was a big.
no, that's a dangerous thing to say.
Well, think of ants on your balloon
Yeah.
or people on the surface.
If we're one of the ants on one side of the balloon and we're actually looking right through the center of the explosion and all the way over to the other side of the balloon and see something that's
But
going
you
on.
don't know the balloon is round. All you know is the balloon is flat.
Well, I'm just saying it might be an idea. We're not at the center of the universe like Copernicus, you know, like it's the same thing. Like we always think we're at the center of the universe, but we're not. You know, we're likely over to one side of it.
Well, there isn't one side, that what he's saying is, the problem is that, and it's your talk, but the problem is that we can't really talk about the shape of the universe because we're used to thinking in 3 dimensions. We need an extra dimension. But if you imagine we had one less dimension and we were on the surface of a sphere, you can't talk about where there's no special point
Yeah.
on the surface of a sphere.
Three-dimensional and some.
And the universe is like that. There is no special point in the universe.
Okay, so let's get away from the location question for a minute.
I don't understand that.
How many times are we gonna say that?
Okay.
Expanding.
Go ahead, Gary, go ahead.
Space as, whether there's preferred direction.
Yeah.
An actual location that's the center, an edge or not, or anything else. What we see is an arbitrary volume. Just based solely on we're here and we can go out so far, right?
Yeah.
So we can't actually touch it, but we can see further than we used to.
Yeah.
And much of cosmology has evolved from not much better than fantasy through to what could be considered real theories and testable theories. And now we've actually got enough data to put a lot of limits on those theories.
Yeah.
Okay. So it's becoming more of a physically meaningful piece of science.
Yeah.
Distance involved a lot of measurements. Some of those always come back to time, right? Like how far back in time is it?
Yeah.
Einstein, when he did well, general relativity and so on.
Yeah.
And then special relativity, I guess. Ultimately, he said, there's no space or time, there's only space-time. I haven't read anything, I read a lot, but I don't understand much, but I forget a lot of it too. But I've never read anything that I can recall that has broken that sort of assertion that Einstein made. And when you look at what happens when you get into relativistic speeds, you know, you get all these effects that time dilates, distances shrink, or whatever.
Yeah.
So as the universe expands, in our current understanding, how can space expand without having an effect on time?
Well, I mean, I guess you can,
So I'll just repeat the
Okay,
question
yeah.
for the people.
I'll think while
So
you're.
what we ended up with from Gary's question is, you know, space and time are coupled. How can space expand without having an effect on time? And so back to Ivan.
So I guess,
And of course, the next step would be, well, what would the effect be?
yeah, well, I mean, so.
Anything from nothing to,
Okay, so these cosmological models, they are completely described by exact solutions to Einstein's equations. So they're sort of like geometrical objects that like we know everything about, right? Just like you know what a cube looks like, you know what a sphere looks like. So saying that space and time, you know, that are space-time doesn't mean that they are exactly the same thing, right? So just because you have an expansion in space doesn't necessarily mean that somehow time is expanding as well. But even if it did, you can, I mean, okay, you're going to choose to measure something, right? So because of the way these models work, the basic assumption of these models is that there are going to be these slices of space-time which look identical everywhere on the slice. That's like the Copernican or Keplerian or whatever principle. I guess it's Copernican. I say Kepler, and I bet it's Copernican.
Wonder about that.
Yeah. And then what happens is you have those, then you can take, so any space, okay, so say you have any space-time, you could choose instants in a particular, any way you like. You say, okay, this is going to be my instant of time. There's some restrictions on how you can do that. This is going to be my instant of time. This is going to be my instant of time. This is going to be my instant of time. And then you can measure, you could specify a way to go between these slices. And then you can like measure the time between the slices. And, you know, different ways you can do it, maybe uniform ways, non-uniform ways, different ways you can do it. For these special cosmological solutions, you do have this preferred slicing, and then because nothing's really moving in them, you can move in some sense, it's like moving perpendicular to a surface. You can move perpendicular to these things in time, and you can measure a time in between these things. And so in these cases, and so between each of these slices, there is kind of a, I guess it's probably the minimum, that'll be the maximum. It'll be the maximum maximum time you can measure between two slices. So you have these two slices of time, these two kind of like three-dimensional slices of space-time, and you look at the maximum time that can be measured for any path traveling between them. I think that's probably how it's going to work. That is the time we're talking about here. So and so because the things are uniform, then the space is expanding in this uniform way, but then there's the time is being measured as well. So they're not, I mean, there's a way you can mix them. You could change, you could boost things, and you could choose to measure things differently. But this is like, I guess, how do I say it? Saying that there is not a preferred description selected by the theory, selected by the way you slice what by this preferred, there's no notion of time preferred by general relativity, but this is a particular solution of general relativity that does have a preferred notion of time and a preferred notion of space. I guess that's for these cosmological ones. If you're talking about like black hole solutions or something like that, you don't have that. If you're talking about Minkowski space, you don't have that. This particular solution of the equation does have a preferred notion in it.
So
It does, yes.
So
I mean, okay. And what does preferred mean in this case? Does it mean it has some physical kind of meaning beyond the theory? Well, no, it just means that there's a convenient thing you can do within the theory that kind of matches the description that you look. There's a convenient way to measure within the theory, I guess, is about what this preferred notion of time is. There's other solutions. So these cosmological models assume things are the same in all directions, it's homogeneous, like I said. There's these other ones, and what are they called now? They're called I've forgotten the name. There's other cosmological models where like you don't treat all the space dimensions as the same. So there's ones, mixed master universes. So there's ones where like you have one dimension can collapse while the other dimension can expand. And then they have all kinds of crazy kind of things that happen. There's other solutions to cosmology where like even the space dimensions aren't doing exactly the same thing. So saying that, time and space are somehow, space-time sort of on an equal footing. I mean, they're not completely on an equal footing, but kind of on an equal footing doesn't mean that you can't have solutions which treat things differently, I guess. I don't know if that helps.
Okay. I've got a comment from David Bourgeois. We'll probably have to wrap it up because you need to get back to work.
Yeah.
He pointed out that the 1973 book, many reprints by Misner, Thorne, and Wheeler which is called Gravitation. It's got a picture of an apple, big black book with a picture of an apple on the front, or at least did. Section 29.5 talks about this, and they call it the lens effect. Yeah. So it's in there going back that far. So, and one of the things I think that is really sort of hard for people who are not Ivan to get their heads around is this. I think this is right, that we should think about what we're seeing when we look out into the universe as not the galaxies moving with respect to space. They're actually, the galaxies are all just sitting still in space, but the space they're sitting still in is expanding. So we often think about everything is sort of flying away from each other like an explosion, but that's probably not quite the right way to think about it.
No, I mean, there's Big Bang models there are Big Bang models where you start off with the universe having like zero volume, and then it expands from there. There's also Big Bang models where you start off with the universe having infinite volume and it just continues to be infinite. Right? So there's different, it's not even like the Big Bang happened all at once. Like even apart from the issue of whether there's a center or not, which there isn't. But even apart from that, the Big Bang can like happen everywhere at once, right? And that, there are models like these. So that equation I put up, right? You just take the different constants for those three types of matter and you can solve them. And you can solve these as the second year differential equations course. You can get lots of these exact solutions. You can plot them out and understand what's happening. Like this is if you haven't done differential equations, it's complicated, but if you've done differential equations, this is an easy differential equation. You can solve it in the first course you do. If you have all of them, then you need to do it numerically, but it's still pretty easy to solve them numerically. And so you can kind of catalog the different kinds of solutions, right? And some of them will, have, Big Bang happening everywhere at once, over an infinite region at once. Some of them happening, I'm not sure they have them with finite. Some will have them happening kind of like universe has zero volume at the beginning. All these kinds of things can happen, yeah.
Okay, well, I think we should thank Ivan again. I think whenever you give a talk, it's provocative. So people are going to be.
Let me show you how. And then she talks about cones and so, oh God, all the terminologies have gone out of my head. I'm not a trained cosmologist, I'm a semi-trained cosmologist. But it's intriguing, and it's worth a view. It's worth about 10 views before you understand it. But it's a difficult topic. This is a very brave thing of you to do.
We've been watching some of the new Star Wars stuff recently. And it just bothers me some, you have all these things, but you have faster than light travel and you have anti-gravity. Once you have faster than light travel and anti-gravity, everything's off the table.
Oh yeah.
It makes no sense anymore.
Pure fantasy. I have an engineering friend in Ontario. There's no way to convince him that faster than light travel isn't just an end problem. Anyway, thank you.
Yep, thank you very much.
Okay.
And I think we've successfully navigated the hand back.
Yeah, I think so.
Randy.
Maybe I'll be walking home and you'll hear me still talking.
Okay. So I'll let Ivan zip up and I'm not throwing you out or anything.
No, I gotta go.
Yeah, I figured. Okay, thank you very much again.
We have an accident. I'll use that pencil.
Okay, so I left the announcements till Randy, can you hear me again now? We're good. So the next meeting is going to be Wednesday, May 17th, and that's going to be a members meeting. But we're also going to have a talk from Blake Nancro, who is the chair of the RASC Observing Committee. He's going to talk about some of the observing certificates. So he's going to give us a short talk, but it's a members meeting, so we can also have people giving short talks about some of the things they're interested in, some of the projects you're working on. So please think about something that you'd like to talk about, and Randy's going to talk about some stuff about the eclipse. But pass it on to Randy or send it to info@stjohnsrac.ca, although I suspect everybody's got Randy's email, or to me. And we'd really like to hear from a few more people if we could. International Astronomy Day is going to be May 6th, so Saturday, May 6th. That's the end of International Astronomy Week. Other people are going to be celebrating it a week earlier, but the Geo Center isn't open the end of April, so it's going to be at the Johnson Geo Center. We'll have displays inside and solar observing if it's sunny out in the afternoon, and then some observing in the evening. So watch for details, and there's certainly room for volunteers to help us with that. So let us know if you're interested in coming and helping out with that. There's, as you all know, sadly, Sky News is gone, but the seems like some of the people who are involved in Sky News have set up an astronomy website. It's at www.astronomybynight.ca. I encourage you to take a look at it. It looks pretty good. It looks like it's sort of carrying on the style that the Sky News website had. So it'd be nice to give them some support. And so I'll say this, and you can add, Gary can add anything that we need to, but the planetarium shows are starting up again. Gary Diamond does those at the Marine Institute. And on May 6th, there's going to be a members only show. And this is it, unveiling the invisible universe. It's the first time we're going to see it in this province. It's 8:30 p.m. And it's describing looking at the universe with, from short wavelengths like X-rays and gamma rays up to gravitational waves. And is there anything else we need to know about that? Oh, May 11th. Okay, so everybody make that change. And Randy, is there any way for you to fix that in the recording or?
Just verbally, May 11th, thank you, I was going to say.
May 11th. Okay, sorry about that. Thank you for catching that. Anything else? Seats, members only? Okay. Okay, so now Randy's gonna come up here and say a few words about how to get into RESC NL Talk. Okay.
I think a lot of you are already on the talk group, right? It's more than just a talk group, though. It's also a place for archiving photos and other things. So if you send me an email at any of the addresses mentioned, I can add you. Well, actually, the way it works is I send you an invite and you follow the invite and set yourself up on the site. And I'll just show you that's the front page for it. And we have 31 members. We've had 1,600 posts. We could do other things with this. One thing that people are interested in, and people can search for that tag if they're only interested in that topic. We could do polls, chats.
Do you find this page?
When you log in,
You have to contact Randy
Are you-
and get an invite to join the group.
are you on chat?
How on the top, right?
Well,
I've never seen this page.
but we all can have a different view of what the group is, right?
Marcel knows that. Okay.
I use it only now as well. I see this page maybe once or twice a year.
So,
I use it only through this page and not mine.
Ah,
so this also tells you how many articles there've been by month, by year. Also, other data about it. We have a subgroup for executive mailing, but we haven't been using that yet.
You haven't changed anything in the last month or so, have you?
On the group, no.
Twice in the last month, about 2 weeks ago, a bunch of emails showed up in my junk file.
Oh, that's common these days.
Notice in this meeting.
Gary's getting my emails in spam, right?
No, like you never had before, then all of a sudden in the last 2 weeks, I've already got 8 or 9 emails that I've.
That's probably your email
Yeah.
Well,
provider.
the iPad just had a software update, so I don't know if that
Yeah.
had something to do.
Well, more likely your providers changed their spam rules and those sorts of things.
Yeah,
Yeah.
anything that Randy sends to me goes directly to spam.
Yeah.
I didn't know anything about this meeting until Dave told me to.
I went for links.
And
Meeting.
well, some of your messages I found. Lots back too.
Oh, okay.
I can start sending that. Anyway, let's get through this. So if you go and click on photos on the side there, you'll see that we have 2,500 photos posted. About almost 4 gigabytes of photos. And Mike farms them for a presentation like for tonight. And if you just click on it, you go down through. Again, you can search by topic or posting or
I
date.
use it to move photos from
Yeah.
my computer to my phone too, if I want to show somebody. That's the easiest way for me to move photos around.
There's also,
I've signed into Google all the time.
No, I just bring that up and download the photo on my phone.
So there's also a thing called files. I've stored the last of the newsletters there, for example. So if you click on that, you can download the newsletter. Remember that pandemic issue? And some people, typical message that I get in my email looks like this, right? And it has the picture. If you're getting a digest view, you can set digest in a couple of ways. Digest, you can get a mail every month, every day, every month, and it'll tell you. And again, you can click on those and see them. And it just tells you, like this one, for example, on that topic. Yeah, I know. There's 8 replies to that one, right? We're going to use this function for planning for observing sessions at Butterpot. So this is where Robert will say, anybody going out to Butterpot tonight? That's where we will do that, right?
How do you get to that page again?
Well, if once you log in, or if you get any message,
I've just been getting through the.
okay, so at the bottom of every message, there's a bunch of functions. One of them is reply to message, go to group. See if I can find it here. Maybe you haven't scrolled down far enough in the message, right? Sorry, I didn't print that one. But on the bottom of every message that I get, there's 5 or 6 links. Now, when you go to the group, lost my chart. When you go to the bottom, you can log in. You can log in either with the password that I give you or you set, or you can use authority from Google or Facebook or some of those. That will just get you right to the group as well, right?
I don't sign into those things ever.
Well,
And I'm exactly the opposite. I don't want email. I've gotten way too much email.
Yeah.
So I don't want these things coming as email. I just sign into this a couple times a day. I do get a digest a couple times a day.
and you can look at your own
But you
subscription.
have that option in your settings, you can choose to do all by
Okay.
email, all this way, or have digest.
Okay.
Very flexible.
Yeah,
Yeah.
that's what I do.
Okay.
Okay, thanks, Randy. Okay, so the next thing I wanted to mention is that there we are. The RSC General Assembly, I guess, is going to be before our next meeting, right?
Oh, we're right in the middle of
Oh, and when we're doing,
also trying to.
oh dear.
Coronation of that weekend.
Okay, well anyways, and they were great talks. Last year, you can take a look at the schedule. It's only $35 to register, and you can sort of pick and choose what you want to listen to, and there's stuff on Sunday, and I guess on the Friday, so I'll draw, that, and there is an astrophotography contest. If you go there, you do have to enter by May 1st. Those are the categories. I've listed them there. So I draw that to your attention. And the last thing that came up, there was some, so to read the journal online, which you all should all have access to. I don't know how okay, maybe the internet is being a little slow for me too, so. Oh, there we are. Yeah, so go to publications, journal, and under this index, well, I didn't want that. Oh, now I've closed it. Anyways, you go to the page, publications, journal, and the trick is that, and the latest issue and all the previous issues are there. You click on it, and if you haven't logged in, at that point, it'll ask you for your username and your password for RASC. And once you do that, you can download either a high resolution or a low resolution PDF of the journal. So if you have any trouble doing that, let Randy or me know, and we'll give you a hand with that. It's pretty easy though. Okay, so member observations, I'll just run through these fairly quickly. Okay, so this is all exactly a month ago. Beautiful one from Jim with his new camera. All the details are there. Anything else to say about this one or?
No, I just remember this evening being, unusually cold and, unusually windy. So if you fix a peak, you can see some, your eyes will find that it's kind of blurry, but.
Yeah.
Right.
And the significance here is that it was from Butterpot, but from the gate at Butterpot, not inside.
That's right. It was locked up.
Okay, but very nice. And March 23rd, Venus and the Moon are up, and we have pictures from Cynthia on her cell phone and Gary on his cell phone and Sue Hart with her camera. And let's see, it's not advancing. And the petals had many pictures, some with lovely earth shine on the moon. Always very nice pictures. So that was March 23rd. And March 23rd, so there's another one from the petals.
Oh, just saying.
Yeah.
Gorgeous to look at.
And Robert did the Rosette Nebula that night with an H alpha and an oxygen 3 filter, and that's his stuff is starting to really work very nicely. A lot of detail there, and getting lots of H alpha. And that night, so that it was the same night, but it was after midnight, so it's March 24th. Was the night that we could see the aurora. So Cynthia and I went to Outer Cove, and you couldn't see the colors with your naked eye. You could certainly see the aurora was there. You could see the light in the sky. You could actually see sort of ripples moving. You could see it moving, but you had to use a camera to get the image. And there were some much better pictures than this that people got aroused again and jumped in the car and drove off.
Problem. Is that your internet?
I think it must be my internet connection.
Common request from people, even in Rascal now the past 2 weeks is. Get on bed.
Yeah, I think I'm ready to go to bed and thought, oh, well, maybe there's something going on. So we took a shot at it. And so the pedals saw it too. I think this was from their shot, maybe from Bali. Yeah, there's some more shots from them. And
that was on the.
it's
That was
fun
on
that
roll.
for ours too, it's a little hard to see, but there's Cassiopeia, I think, in our picture. And so it's fun that you can see some of the stars too. There's another, that's a beautiful shot from them. And another one. So they did lots of shots. And Jim with his new camera again, M51. Yep, March 30th. Lovely shot. You can see some of the disruption as well as so there's a lot of stuff in that picture.
There's a lot going on there because of there's really two galaxies colliding. That's what makes this one.
And one's taking more of a beating than the other.
Yeah.
And Gary did some sketching, which was very nice to see. He shared it with us on the chat. So this was the same night. So all of these observations tend to get grouped together because we only have a few nice nights. Did you want to say anything about this one, Gary?
No, I was just too lazy to set up.
No, it's a great
Well,
shot, though. I love it.
I don't think that counts as lazy, something else, but and Robert was down in Florida and managed to get a shot of the moon. I think it must have been April 6th because it looks like a full moon. Is pretty good what's that? Well, that's pretty impressive if that's Mars, but I think it's the moon.
Yes, Mars could be the size of a full moon.
And beautiful, the Iris Nebula with lots of dust and lots of detail and yeah, just really striking. I've tried the sun a little bit. So this was a little more than a week ago, some prominences, some sunspots, and I think a little bit of dirt. And John Nugent also did M51, the Whirlpool Galaxy. I had to crop that a little bit I did crop it a little bit so that I could make it look a little bit bigger here. But that was posted on the talk channel. Very nice, John. I guess John's still there. John, did you want to say anything about this one?
No, not really. I just tried bumping up the ISO like Chris had suggested to test it out. See what it's
hang on, he's speaking, but I'm not hearing him. Okay, just hang on for a second, John. Are you hearing him? I've got the speakers turned on. Let me see what I've got going on here. Okay, now try, John.
Can you hear me now?
Yeah. Okay.
I didn't have much to say about it anyways, but I was just trying out the ISO 3200 like Chris has suggested.
Okay.
Just see how it looked.
It's very nice.
Thank you.
Okay, thanks. And Gary posted one a few days ago with his Comet camera, which I always love these pictures with not Comet, Meteor.
All sky camera.
Well, it's not all sky, right?
No, just a section.
It's a little bit of the sky. How much?
30 degrees, I think.
Okay. So you gotta be a little bit lucky to get some meteors there.
The Big Dipper and the Little Dipper constellation, so I don't like that expansion. It's
Okay.
Is it tonight? Base garbage is coming in?
so
Recently coming in tonight. So 2 hours of the tracker.
Well,
Gary, is that's a double meter out?
yeah, that's the double meteor. I got.
It's supposed to be Cassiopeia?
Yeah.
Okay, excellent. Yeah, that's for
Now, the
one.
night before, I got two right close together, going the same direction.
Yeah, no, they're like these were right parallel about the W, and I was like, wow, that must have split somehow in the sky.
Isn't it this Friday or just sometime this week?
The Earth.
Yeah,
Yeah,
and there's been a lot of activity. But I think I also sent another one, just showing you all the,
yeah, I didn't post that one, but
well, it wasn't what it said, it was just full of satellites.
yeah. It looks like there's a couple in here too.
Yeah.
Yeah, so yeah, it seems like there was a real burst of them for a couple minutes there and then nothing much before and nothing much after. So that's cool. I've been working on the Markarian chain in Virgo, and it's just fun to see lots of galaxies. So
brought down to 2.
yeah, this is that one, I think. Yeah. And that's it. Robert just flew back and he sent me an email just before the meeting started that he was tired. And so I think this is posted, the sky this month is posted. But I think we'll just sort of leave it there and people are okay with that. So to wrap up, just a reminder that we're having a members meeting next week, plus some information about the observing certificates. But I'd really encourage people to think about something they might want to talk about for a couple minutes. I'm sure there'll be a few takers on that. And Randy's going to talk a little bit about an interactive eclipse map and some stuff about some planning with that.
Planning.
Planning, yeah. Okay, well, thank you all for coming out and thank you online for sticking with us. Oh, I just killed it. Oh, no, that was screen sharing is stopped.
Let's see.
Interesting. Well, this one's still working. No, my computer's still working. Oh, there you are. Oh, I think it's this cable's a bit loose. Okay, so I think thanks to Randy. I think we've got some refreshments. Interesting meeting as always. Thanks everyone. Thanks for coming, Sue and everybody else that's on there. And it's nice that we're getting some participation from the online folks as well.